Hi everybody, so we're going to continue what we did previously, so I'm just going to do a reminder. So we're in the class, of course, of physics 2, and what we did in the last episode, we talked about Gauss's law. Gauss's law, and today it's going to be more a practical tutorial, right? The previous one was kind of introduction because I know it's a sensitive topic in the class. So what we did was we had a problem of a submarine. So I'm going to draw again the submarine. So here it is. We have this periscope that help us see what's going on above water. We have it here, and the submarine have some propeller, windows, and what we talked about is that the wall of the submarine is actually charged. By which amount? Say it's only positive, and the charge distribution, it's a volume distribution, you see? It's a volume distribution. Come in, just a recap of what we did previously. And the distribution of charge was some constant multiply by x squared d squared. And I told you that if you're going to look at the wall from different angle, let's give us the axis because I already put here x squared. So this is a function of x. So this is our coordinate system. This is z, this is y, and this is x, right? If we're going to look from the side on the wall of the submarine, it's looking like this. This is you inside, right? Looking through the window. Let's say this is a window. And this is a fish. And my system coordinate is going like this. We have z, right? And we have x. Okay? And if I wanted to be a proper axis system, this should be y, going into your face, right? And I know one of the problems with Gauss's law, it's all the 3D thing. So I actually brought this. So this is going to be our wall of the submarine, okay? This is me inside, fish here, right? Okay? And this is the thickness of the wall, which is given is d. So this is d. Okay? So how the charge is distributed? Most of the charge you see is growing in a parabolic fashion, and it's more strong on the walls, right? But you still have some charge in the middle, right? In this fashion. You see it? Even in this fashion, it's zero in the middle, right? Do you understand how the charge is distributed? Mostly on the edges, but you have some in the middle. Good. And we ask, what is the direction of the electric field? And we explained it previously, that the direction of the electric field must be at the x direction, right? We talked about it, that if we're going to change orientation again and look at this is x, this is z, and this is y, we said that for every contribution here, and there's another contribution on the other side. If this is plus z plus y, this is minus z minus y, and the contribution for a fish over here gonna be only summation at that direction, right? Sorry, this one gonna produce electric field and that direction, which can we project to these two. This one is actually these two, and this charge over here gonna make electric field at this direction, and if you're gonna project it, it's gonna be in that direction. That direction, these two dies out, and these two sum up. Okay, so the only valid explanation for what is the direction of the electric field must be at the x direction. So we talked about it, that E direction must be at the x direction, and this is because of the infinite symmetry, okay, of the wall. And the other thing, and also we know that E must be a function of x, because the wall look to the fish as a uniform wall. There's nothing that's changing in x, y, in a z and y, only at x direction. Okay? That's a concept. Is it clear? You have any question about it? Okay, so now we're going to move to the next one. Okay, camera here. Okay, so the next question gonna be not is what is the direction, but what is actually the size of the electric field. Okay, good. So what is, so this question 1, right? So this is gonna be let's say 1.1, right? 1.2. 1.1 was this. What is the direction, which we covered previously? And right now we're gonna deal what is the magnitude of E, right? Because a vector as the electric field build of a magnitude and a direction. Okay, every time you know the direction of the electric field, you already know it, you don't need to think about it. You see the symmetry, you understand what's going on, this is the time to use Gauss's law. I'm going to that board, so I'm gonna remind you what is Gauss's law. I move this distribution function to here, square divided by d square. So what is Gauss's law telling us? I love to think about Gauss's law as geometry versus sum of charge. That's how I see it in my mind, okay? So the geometry is actually state some area which have some flux. So we have this term here, right? And we're gonna understand really good what these terms mean. And the other one, this is the geometry, right? Geometry of the problem. So this is really good if you know what the direction of the electric field. Okay, really useful. And this must be, let's do it in that manner, like I like to think about as a link. We have 2 steps to solve this. Okay, so the other part is actually understand what is the charge inside divided by some constant, right? Epsilon naught, right? So this is actually tutorial 1. What we did, we count charges. This is a new method to find electric field. So we know this is always hold. This is Gauss's law. It's a fundamental law of nature, okay? Good. So we're gonna try to use that. So let's try to solve this concept. So we have this giant wall, right? And we know that the direction of the electric field is only at the x direction. Here it's to the positive, here it's to the negative. It's the same problem, but the negative sign, right? X is a right, X is a right. Okay, good. So the best way to solve Gauss's law is first to understand what is the area that I actually want to make. Okay, the area is your free choice. It's an imaginary area. Okay, so if I want to use this symmetry, probably I'm gonna use the same geometry. So this is gonna be the area that I'm gonna choose. Okay, so I want to know what is the electric field, let's say, in this part. Okay, so I'm gonna produce imaginary box. Here it is. The box is imaginary, the wall is real. And shove it inside at that way. Okay? Understand what's going on? Perfect. So let's put this aside and we're gonna talk about that. Okay, good. So I want to calculate first what this integral is actually equal. I must choose, thank you, I must choose, shirt all the board. I must choose here a closed area. What is the closed area that I choose? It's this 3D, right, shape. So I'm gonna draw here. You don't have to do it, right? I exaggerating, right? I actually do this. But if you're just gonna do a circle, it means it's a closed area, it's valid. Here we're gonna put E, okay? E, the magnitude, right? Which I don't know, and it can vary with x's, many x's, right? Multiply by this, the dA, yeah, I can write it this manner, you know, without the vector notation, which means this is only the magnitude, and multiply, it's a dot product, right? So I need here to have cosines alpha. Perfect. So we need to figure out what this is equal to. And I want you to notice, if this is the wall, okay, I can take this volume and divide it into this area and divide it to its part, right, subparts. I actually notify here 4 different, I see 6 different faces, right? You see it? 6 different areas. So I can actually take this thing and open it. Now I cannot put here the form of a circular because I open it, okay? And I have here, I have this thing, right? Which is the lids. Here it is. This part, right, of this thing. I have 2 of those, right? Let's do here 2 of those, right? Which have E at the location of the end of my volume. And let's do here a drawing. So this is the wall, and this is the imaginary volume that I use in order to find what is actually the electric field on a fish over here. What is the magnitude here? Okay? And I'm gonna say that this size of the box is actually gonna be L. Okay? So the 2L. And that means that the electric field at this part, right, is just L. Agreed? L plus minus L actually, because if we thinking about this, that part, right? So it's a minus L, right? dA cosines. What is the cosines here between them? I want you to see. So this is the wall. I'm the wall. This is penetrate me, right? What is dA? Remember, dA is a small unit of area, which is a vector, have a direction, right? Which is kind of the nose, if I'm going to think about that way. This is a dA, and you have some nose, right? So a smiley. So this is the direction of these dAs. This is the direction of this dA. What is the direction of this dA? At the x coordinate, right? We said this is x, this is z, and this is y. Agreed? So the angle between them is actually 0, because the electric field also points at that direction. Is it clear? For both of them, right? Here dA pointing at that direction, here dA is pointing at that direction, right? So dA also that direction, dA is also the direction. Is it clear? Okay? It's okay? Understood? Good. What we left with? We have the other sides of the box, right? We have this one, this one, this one, this one, right? So we have 4 of those, right? 4 of those. And this is equal to what? To E in various sizes, right? I don't know, it's different x's. It's not only plus and L, it's this. It's what's going on all over this place. It's clear? There are many electric fields changing. Okay, because we know that E is a function of x in the direction of x because of the symmetry. Good. We have here dA. And what is the angle between them? 90. Exactly, 90 degrees. So if I'm going to look at this smiley we drew up before, I know the electric field is at the red direction, right? Only at x. And dA is actually what? Projecting at u. And what is this dA? At the direction. And x and the electric field at that direction. And for that side, the same thing, the same thing. So in all the other angles, we see that, in all the other faces, we see that the angle is actually 90 degrees. What's happened to this integral? 0. It's dying out, okay? So the concept of Gauss's law is actually choosing a smart area, imaginary area, okay? This is the first part of the formula, right? This is the first part, okay? The first part is to choose a smart area, this one, in order to use the symmetry to make usually one of those. Angle 0, angle 90 degrees, killing the integral or killing the cosines. That's the idea, because this is equal to 1, right? So this is the concept. So what we left with is only this. We have 2 multiply by E at the location L, right? Multiply by the integral dA, right? That's what we left with. Camera, see me? Good, okay? That's what we left with. So this, what is this integral? It's actually calculating some area, this area, right? So it's actually a two-dimensional, it's an area, and we're calculating a small contribution. Remind you, this is Z, this is Y, right? So it's a small chunks of dz and dy, right? Small chunks that are gonna build this part, right? So I have, where is it? Maybe inside. Good. So I have this thing, okay? So this is actually, you know, this part, okay? So you can give it to everybody. Show it to everybody. So this is kind of what we're actually doing. So this integral is dz, right? dy, and this size, I need to know what the geometry. So let's say it have some height h and some width of w, right? So this is actually wh. This is the size of this area, right? Understood? So in general, this term is eventually E, which I don't know, 2 and WH. We finish half of the problem, and it was the hard part of the problem. Okay? Good. So right now, after doing the left side of the equation, I'm going to that place. After doing this part of the equation, we want to say that this is equal to that part. And that part, it's easier to solve, okay? So let's go and do that. So now we want to calculate what is actually the charge. So we made up this area, and Gauss's law asks us, okay, good, you have an area. I want to know what is the charge inside this area that you had in mind, okay? So this is just a constant, right? And how we can find the total charge? Q equal to the? Exactly, the integral, sum of its parts. So we actually want to do this thing. Sum all the small chunks of charge that we have inside the volume. We have a closed area, right? Which actually have inside a volume. And this volume have some charge in it. If we're going to know this charge, we can compare it to this side of the equation, and we kill the question. Good. So dq is equal to what? Do you remember? In our case, two things. The charge density, right, which is rho, in our case is equal to rho naught, x squared divided by d squared, multiplied by the volume integral, right? The volume chunk, right? dv, which in our case is Cartesian, okay? dx, dy, dz. Everything is clear? It's good? All good? Good. Okay. So what is actually this charge? Is actually, look, it's this one. Where we have charge here. You see it? This is kind of the charge that we have. It's all over the box, right? It's inside here. Here we don't have any charge, only inside the wall of the submarine. So I want to calculate this thing, this charge. Okay, so what is the integral boundaries? So we have here three integrals, right? The one that deal with dx is starting from minus d over 2, right? Until plus d over 2, right? Sum all the wall, right? And here we have just the height of this and the width of this, which we just made up, right? So this is actually going to be 0, w, 0 till h. Clear? Constant can go out, right? This is also a constant. Good. And these two are actually not relevant to the integral. This is x squared, you see it? So it's just multiplied by hw, right? And then I left with this integral, x squared dx plus d over 2 minus, plus d over 2 minus d. Yes, we got it? Good. So this is integral equal to what? if you're gonna do it, it's gonna end up to be 2HW rho 0 divided by d square, 2HW rho 0 d 24 epsilon 0, okay? And now we found that thing previously. Right now we just found that, and the last thing we have to do to finish is to compare them. Understood? So let's do this thing equal to what we found over there, must be equal, let's do it like this. This thing, which is 2HW d24, equal to the other side of Gauss's law equation, which we found to be EL multiplied by 2HW. Right? That's what we found. And what we are getting, we see that it doesn't matter what is the end of the shape that we choose. You see it? A 2HW, the leads of the box actually vanish from the equation. You see it? And we end up with E, the size of the box, right? Equal to, so it like this, equal to rho naught d 24 epsilon naught. Okay?
Should be an L, right?
What?
D should be an L.
D should be an L? No, D should be a D. Because D came from here.
Okay.
You substitute. Yes, Maya.
Where did the d over 2 came from?
What?
Why minus d over 2?
Okay, so if you look at our axis, okay, so this is this way. This is D. This is D, the thickness. So we start to accumulate charge from minus d over 2 till d over 2, right? Plus, okay, so this is the reason. And H and W was something that I invented, right? It was my box, my imagination. I can do whatever I want, okay? So this is actually the electric field. Let's go here. So I'm gonna clean this part. Camera see me good? So let's sharpen the question, okay? This was, what is the electric field? Electric field in the zone, L is bigger than X bigger than 0. Bigger than d over 2. Okay, that's what we found. We found what's the electric field outside of the wall, right? And this is also true for X minus, it's only true for the other side, right? So we found that the electric field at these regions is actually equal to this. And this is kind of a weird result. Why it's a weird result? This is a constant. This is a constant. 24 is a constant. And epsilon naught is a constant. The electric field outside of the wall is a constant. And the answer is yes. Why it's happened so? Because we assume, and it's what's happened when you assume this kind of stuff, that if you assume a huge wall, so think about this thing as I got the fish. So think about the fish, and he's look at the wall, and he see infinite wall at Z, infinite wall at Y, right? So this picture for him does not that much changing from this picture point of view. So he actually sensed the electric field all around the same. That's what happened. This is the assumption we took. Where it's all, think about the coronavirus, for example. Coronavirus in some glass, see charge on the glass. For him, the wall is infinite. It's huge. You're gonna sense exactly the same amount of electric field from it. Okay? If it would not go far away, right? Okay. So this was a little bit intuition, but we still did not found all the electric field all over the world, right? We did not found, and this is going to be our next question. So this is going to be 1.3. Is what is the electric field size inside the wall? Okay. Got it? Okay, so how are we going to do it? We're going to do the same idea. So if you did not catch up what we did before, we're going to do the same thing, the same concept. Okay, so I have this wall. I want to use Gauss's law because I know that according to symmetry, electric field going to point only at the x direction and be dependent only at x. So I want to use this symmetry, and I'm going to use some, let's say, this shape. Okay, this one. The same idea here. Something that is inside, a little bit shorter than that would be better. I don't see. Okay, never mind. But imagine that this thing, actually it is a little bit shorter. Okay, I'm going to put the box inside. And right now I'm going to do the same thing, but my plus L and minus L actually inside the volume of the wall. Okay, you had a question? Okay, perfect. So I'm going to do that again, the same concept. Okay, so I want to clean that. So I want to write the left hand side. So I'm going to choose this kind of volume, right? I'm exaggerating, right? I just want to say this is a closed volume of many sizes of E, many sizes, many dAs, and many angles, right? I don't know the angles between them. Many different angles. But then I'm going to open this integral, and I can open integral because it's a summation. 1 plus 1 plus 1 plus 1 is 4. I can take 4 and split it into different parts, right? And I'm going to say I have two leads, right, which have E at the location L, right, multiplied by dA, and the cosines between them, it's going to be 0 because it's going to pointing at the direction of the lead, and dA going to point in the direction of the lead. Perfect, okay? So this is 0. And this is 1. So, and what we left with? We left with 4 of those, which we have E in various places. Many axes inside the wall, many of them. Yes? Multiplied by dA, but for all of them, the same phenomena happen. E is pointing in that direction, and one of the sides going to point in a perpendicular direction. Okay? So this is a 90 degrees. I don't care about this integral. It's dying out. This is a constant, can go outside of the integral, right? And the size of the area, right? This size, if we're going to sum all the dA, I'm going to end up with HW. And don't forget that we have 2 of those, right? So we're actually going to have here 2. Finish, killed it. We found the left hand side of Gauss's law, and then I'm going to use the other part of the equation. I'm going to go here, go here. So something is changed. I want you to be careful. Something is changed dramatically now. Now we're looking at a box. If we look at this, that is smaller from the wall. So yes, I still going to go at height of H. I still going to go inside the board with size of W, but what happened to X? Right now I'm not going from the end of the wall to the other end. I'm going from the size of the box till the other side of the box, right? What happened previously? Previously, if this was the submarine wall, we actually go from here to here, but from here to the wall there was no charge. So we sum actually zeros. There was no any reason to put in the integral this part. But from here to here, we had charge. And from here to here, the same again, 0 all the way. But now, the wall is actually bigger than our box. Now we're in this situation. This is the wall of the submarine, and we sum from here to here. This is clear? Good, okay? Because this is the places that people do mistakes in Gauss, okay? So if you feel more confident about that, good. So, okay, sorry, let's clean that. Clean that. So the only thing that has changed is the limits of the integral here. This stay the same, right? HW epsilon rho d squared, right? Right now we are running from minus L plus L. Right? And we're going to end up with H W divided by epsilon naught d square 2 L to the third divided by 3. That's what we're gonna have. Okay? And now what's the idea of Gauss's law? What we need to do right now?
The other side.
Exactly, we're gonna compare this one, this thing that we just found, with what we know. We're gonna compare S. This is, I think about it as G is the geometry side, and S is the sum of the charge. Okay? Understood? This is this part and this part, and we're always gonna compare them. Yes?
Aren't we missing a P0 in the expression, maybe?
What are we missing?
Well, P0.
Yes, thank you. Okay, so we're gonna compare this one to what we found before, which was the same as we did in the previous section, right? Look, this is a different L because we have different box right now. So this is HW multiplied by 2, and what we see again, that what cancelled? This term, right? And what I want you to notice is that sometimes there's not only one shape that's going to solve it, okay? In this example, if you would choose a cylinder, it's going to give you the same result. And for that reason, this thing is actually vanished because you have some freedom in your method of solving it. Let's go to this place. So, if we compare them, we're going to find out that the electric field, and this is, I remind you, it's electric field that actually take care of plus d over 2 divide, and here minus, right? This is the size of the box where we looked. This is the only electric field that survived the equation, and this is equal to rho 0, rho 0 divided by 3 epsilon 0 d to the 3 multiplied by L to the third. This is the electric field that we found. Okay, and right now what you can see, yes, it's changing with the distance, right? This could be thinking as L, as a X, right? This is E, X from plus d over 2 minus d over 2 equal to this constant, right? And this X. That's what's going on inside the submarine, okay? Good. So right now I want to practice the concept, this concept again in a different way, okay? You see this thing? What's the name of it? You know? Of a submarine, this part? Periscope. Periscope, right? Peri, it's looking around. Scope is view, right? Like telescope, look far, right? So we're going to solve the same question about this periscope. We're going to do it more easy, but the same concept going to hold. So let's clean the board. Good. So we're going to focus on the periscope. So right now the fish is looking at the periscope. This is the periscope, and it's shallow. It's hollow in the inside, right? You have the different diameter, the different radius A, and this is B. And let's be easy. Right now, rho is constant, right? It's the same everywhere. It's just a constant. So the first thing I want to ask you, first of all, see that this is kind of an infinite cylinder because the fish is really small compared to it. Okay, that's the idea. So this is the fish. The fish is over here, and it's observing this periscope, right? So the first question I want to ask you, this is like kind of question 2. So this is going to be 2-1. What is the direction of the electric field? Okay, what is the direction of the electric field outside of the cylinder?
Radial out.
Huh?
Radially out.
This is true. So look at that direction. So if you're going to take this and these charges, we're going to see the same concept going on. That's going to point in 2 different directions. They're going to sum up here and going to cancel out over here. Okay, a top view, it's going to be the fish here, right? And you're going to see this and this, right? This gonna sum up here and cancel up here, right? So this is the radial coordinate. This is the radial coordinate, right? Here we compare it to the z. We see different z, delta z and minus delta z. And here we actually compare different theta, right? Different angles. So we have a symmetry all over the cylinder, okay, an angular symmetry. And here we have an infinite symmetry, okay? So again, I hear the word infinite. I hear the whole word symmetry. I said, okay, Gauss's idea. Okay, that's what I want you to feel when you're in the exam. Blah, 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 blah. Infinite cylinder. Infinite plane. Okay, okay. This is the red bulb for Gauss's law probably. Okay, that's what I want you to remember. Okay, so we found that it should be radial, and it's also dependent on the distance from the wall. You understand it? This is the only one that we are going to be care about, right? Because the z effect going to cancel from the other one, and the theta effect going to cancel from the other one, right? Because we have a symmetry. So we know that E must be some magnitude, I don't know what is it, but it must be a function of R in the direction of R, for sure, okay? I understand what is the direction of the electric field. Next step is, what is the magnitude, right? So what is the magnitude of the electric field? So I'm going to use the same concept. So right now, here, I have a periscope, right? So which shape area I'm going to choose to fight this cylinder? You have any idea? Right. If I want to use the symmetry, 99% of the time, fight with the same idea. Okay? Bring them back what they give you. Okay? So I'm going to use this cylinder, right? So we're going to put around the cylinder with the radii R, capital R. Okay? So, good. So we're going to do the integral, this integral. The integral of the closed volume, this one, which have a lot of electric fields in many locations. R. They all multiply by some chunk, right? Some size, area, right? And they all have some angle between each other. But I can open this integral into two distinctive parts. First of all, we can look at the leads, right? This is the leads, right? What are the leads look like? I'm going to take this. What is the direction of the dA? And down below? The camera, not with me. Okay? So this is the size, this is the direction. We're going to take this integral, many location of E, many multiplication by area, and each one have a distinctive angle. And then I'm going to open the integral and say it's built up of two open surface, not closed open. This is an open, okay? I look at the lead and I see this is the direction of dA. What is the direction of E? Radially, right? Radially, radially. The same thing here. Down, 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 and radial, radial, radial. So I know, dude, there's a lot of electric field. In the middle, R equals 0, some centimeter here, some centimeter here, many locations, many dAs, but all of them have what angle? 90 degrees. When you reach 90 degrees or 0, you said, okay, good, I'm in the right direction of solving Gauss law because I cancel something, I use smartly the symmetry. What we left with? The envelope, right? The body of the cylinder. We end up with the envelope and I'm gonna open it up, right? I can take this paper, right? This is the envelope and I can just wrap it up like this. You see? This is what I left with. I took off the lids, right? So what is the height of the cylinder? I choose it. It's my cylinder. It's from my imagination, okay? I'm gonna give it H. What is the length, the parameter of this cylinder? 2 pi, and R is mine. I invented it, right? 2 pi R. And if they ask me what is, this is 2. They ask me what is E for R bigger than B, right? This is the question, the size. So I'm going to choose some R which is bigger than B, yeah, because I want this term in my equation so I can solve, right? So this is going to be here, only at the location R, only here, only at that location, not inside, not outside, okay? So what is the direction of E? We talked about it, it's radial. What is the direction of A? Also radial, right? If we're going to do here a smiley, this is the nose, radially outside, right? And remember, DA is always pointing outside of the volume, okay? Good. So we have here DA multiplied by 1, because the angle between them is 0, cosine of 0 is 1, kill it, okay? This is a constant, right? It's only the electric field in the location capital R. Good. So I'm going to go here. I'm going to go here. They see me? Okay, so this is equal to E at the location R multiplied by this size, H multiplied by 2 pi R. And this is equal to what? To all the charge that we have inside. Now I use the other part of Gauss's law. Okay, this must be equal to all the charge inside A divided by epsilon, right? What is this charge? How are we going to calculate it? We can do the integral, but we had here something that made our life easy. What is the charge distribution? Constant. So we're going to end up with integral, yeah, on dq, which equal to rho, which is constant, multiplied by dv, right? If this is constant, it can go outside of the integral, right? And we only care about what is the volume of this. Understood? What is the volume that actually have the charge? Let's go to this drawing. So we said that the charge is only here, right? You see it? And by the way, this is our Gauss's envelope, Gauss's area, right? It was this. That's what we did, right? So we care only about the charge that we have actually here. You see it? This charge. Also this. Well, we don't have a charge in the middle. This is the place, you know, that you look from the periscope. You look at it, and the light go inside, and you can see what's going on outwards, right? So here there's no charge, there's nothing but air. Going back here. So this volume is actually equal to the size of this hollow cylinder. So it's gonna be, we didn't see, we say it's H. So it's H multiplied by pi b squared, right? Minus pi h pi a squared, right? This is the volume. Understood? Understand why? Yes? It's the whole thing minus what is empty, right? The big thing minus what is inside. Gonna give me this. Good. So we found everything. This is equal to h pi b squared minus a squared divided by epsilon naught, and this must be equal to ER, which we are trying to find, h multiplied by 2 pi r, right? Look, pi is cancelling out. The radius,
You're missing a row, I think.
what?
You're missing row.
Yes, thank you. That's what I was thinking about. Missing row. And what we actually have is, I'm going to go here. I'm going to clear this. So we found out that E as a function of R equal to rho 2 pi R b squared minus a squared. Good? Did you understand what we have done? Okay, nice. Okay.
Does the pi not cancel?
What?
Does the pi cancel out?
Yes, it's cancel out. Thank you. So what I'm missing here? Sorry, is this. Yes, thank you. Good observation. Good. So right now I can ask a similar question. Okay, what is the electric field? Not outside of the periscope, right? Inside of it. Look, not outside, but inside. Okay, in the wall. Inside the wall, not the empty space, the wall. Okay. So this is equal to. This thing gonna change. It's gonna be the same, right? It's gonna be ER multiplied by H 2 pi R, right? If you are looking for what is E for R in between B to A, that's what you're trying to find out, what is the magnitude. So the same left-hand side of the equation gonna stay the same. Understood? Yes? I'm gonna have leads, they're gonna cancel out, and I'm gonna have the body of the cylinder, which is gonna stay because dA and the electric field only pointed radially. But the charge gonna change. What is the charge right now? It's similar concept, but right now we have a smaller outer shell. We don't have B, right? We have H pi R squared, right? Because we are inside of it. This is the cylinder. Camera, see me? This is our cylinder. It's in the middle, right? Minus H pi, the small one. This is the only thing that have changed. Understood? Good. So we're gonna clean this. So if E is talking about R to B, it's equal to, I'm gonna divide by that. Gonna end up with rho 2 epsilon R minus A squared divided by R. Okay? Understood? I just gonna make sure there's no class after us outside. Good. You have an extra 5 minutes to finish the question. Good. I want you. Can you hold it? Save the box. Don't open it. Okay? Don't open the box. Okay. Good.